Questions? Ben? 12. This guy? Okay. So the final score in a soccer game is 4-3. How many different halftime scores are possible? So what this is saying is if the final score on the board was 4-3 for whoever, what might the score have been before that? And it could have been 4-3, couldn't it? It could have been 0-0. In fact, on the scoreboard, oh, that was a mistake. On the scoreboard, doesn't matter who the teams are. If this ends up being a 4 and this ends up being a 3, the fact of the matter is, in terms of the fundamental counting principle, there are a total of 5 different numbers that might have been in this place earlier in time. It could have been a 4 at halftime, it could have been a 3, it could have been a 2, it could have been a 1, or it could have been 0. It could have been a monumental comeback. Over here, there were 4 possible, I don't want to say outcomes because we're traveling backwards in time. There were 4 possible numbers that the losing team could have had at halftime. They could have had 3 goals, they could have had 2, they could have 1, they could have had 0. And that including the 0 becomes important. So the answer to the question is 20. Okay. I want you to cast your mind back now to the ice cream example from yesterday, where I said there were, correct me if I'm wrong, 2 cones, yes? 3 flavors, and 2 sprinkles. Do you remember me telling you that you have to have sprinkles? That's the way it is. No sprinkles? No ice cream, go away. But what if you had an option of not having sprinkles? If you have to have sprinkles, and presumably you're having an ice cream cone, so you definitely have to have a cone and you definitely have to have ice cream. The answer was 2 times 3 times 2, right? But if you could decide not to have sprinkles, the answer would be 2 times 3 times 3. Because for the sprinkles, you now have 3 options. Chocolate, mint, or no thank you. Anyway, does that help? Okay, other questions? Go ahead, Makai. 10 on the second one? Okay. How many different sums of money, and this is going to be kind of connected to what I was just talking about, using at least 1 coin can be made from 5 pennies, 4 nickels, 2 quarters, and 5 loonies. So you have 2 pennies, you have 4 nickels, you have 2 quarters, and you have 5 loonies. So imagine that I've got all of this on the table. And by the way, we have to pick at least 1 coin. You can't say I'm not going to take anything. And you have it in a bag and you reach in and you grab a bunch. How many pennies might you have grabbed? Well, you might have grabbed 2, you might have grabbed 1, or you might have grabbed none. There are 3 different numbers of pennies that you might have picked. So I can pick for the number of pennies any one of 3 different choices. None, 1, or 2. So because we're including the fact that you don't have to have any pennies, we add 1 to the number of pennies there are. And then, of course, we're going to have for the nickels, we have 4 nickels, but that means you have 5 options for how many nickels you choose. You can choose 1, 2, 3, 4, 5, or none. 1, 2, 3, 4, or none, rather. For the quarters, 25-cent pieces, it would be 3. And for the loonies, it would be 6. Do you follow that logic, everyone? Okay. So what happens if we multiply them? If we multiply them, we don't get the right answer. We don't. We get, is that 170? No. No. 45, 270. 270. And when you look at the answer is 269, and the reason is you have to have at least one coin. You can't build in that condition of having at least one coin into your work, but you can build it in at the end saying of these 270 combinations of coins, one of them is no pennies, no nickels, no quarters, no loonies, and that one single combination is not allowed, so we remove one from 270 to get 269. Good? Julie, you had a question?
Number 6 on page 4.
On the first one? Okay. So there are 7 horses in one race and 6 in another race. For a person placing a bet, how many ways can the winners of the 2 races be chosen? So, you know, you have the 7 horses in the one race, and they have names, right? And if I want to pick a winner, I think the word winner is deceptive. You need to know something about horse racing and betting. What this is saying is, if you were to bet on a horse out of the 7 that was going to win, how many different bets could be made? How many different horses could you decide are going to be winners? And the answer is 7. Right? There are 7 horses in that first race that could be winners. Alfred, Barney, Christine, Denise, etc. A, B, C, D, E, F, G. And there's another race, maybe at a different racetrack or at a different time. There's another race that has 6 horses. Well, how many of those could be picked as a winner? The answer is 6. So the answer is going to be 42. And, you know, ultimately, I said this yesterday, these questions are always kind of recycled versions of questions we've seen. This is Bobby Bear picking pants and shirts, except you're not picking a pair of pants out of a pool and a pair of shirts out of a pool. You're picking a horse out of a pool and you're picking a horse out of another pool. Does that make sense? Okay. Other questions? Go ahead, Farhan. 14A? How many 3-digit numbers have digits that are all different? We need to appreciate that when we talk about a 3-digit number, and sometimes we'll see the word number, sometimes we'll see the word numeral. You cannot have a 0 in the first place of a 3-digit number, because then it's not a 3-digit number, it's a 2-digit number. There is the added condition here that all of these digits, I better be careful because I didn't read one carefully enough last time. These are all different. Okay, so cannot repeat. So how many different choices do we have for the first blank? Which we should do first because that's the big condition. The answer is 9. Because you have to pick a digit that's either 1, 2, 3, 4, 5, 6, 7, 8, 9. You cannot choose 0. Now the question is, and we cannot repeat. So think of this as when you write down the digit in your head, you're going to erase it from the pool. You're going to cover it up. You're going to throw it out. Maybe they're Scrabble tiles, although Scrabble tiles don't have numbers. The question becomes, after you've used that non-zero number, how many options do you have for the second place in this 3-digit number? And the answer is you still have 9. You have the 0, which wasn't in your pool of acceptable values to begin with, plus you have the 8 other ones you didn't choose. So this is 9. And now what you've done is you've put a digit of the 10 in the first blank, another digit of the 10 in the second, which leaves only 8. So I don't know what that's going to give. But that will be your answer. $648 maybe or something. Yeah. Other questions? Go ahead, Ryan.
Number 9.
On the first set?
Yeah.
Okay. Now we have to use a bit of our knowledge of the real world. We know that phone numbers have numbers that can be repeated, right? You don't say, well, what's my phone number? 387-5225. Whoa, you mean you have two fives in that phone number? That's allowed. But there are some other conditions here. The first digit cannot be a 0 or a 1. But we can use, there's no other restrictions anywhere else. So if we have the fundamental counting principle saying we have 7 tasks to do, it isn't that Bobby Bear needs to pick a pair of pants and a shirt. He also needs to pick a belt, a pair of shoes, a pair of socks, whatever. Eyeglasses, whatever. We have 7 things that need to be done. The first digit is not a 0 or a 1. That is not allowed. But it can be any other digit. And there's 10 digits in our math system, so that means we have 8 here, times the number of ways to complete the second task will be 10, 10, 10, 10, 10, 10. Because there are no restrictions on any further digits. We can keep using the same one again. We can use any number of the 10 digits. So it's going to be 8 million. Is that okay? You're welcome. Other questions? Okay, I would encourage you, regardless of how many of these you tried or completed, to keep going back to them as a pool of questions that you should, pick some that you didn't do and try them later. And then later, try some more that you didn't do. Remember, practice makes as close to perfect as we can get. So we're going to be moving on today and looking at the second lesson from section 11.1. Again, I've chosen to take 11.1, which is one section. There's a whole lot of things taught in that one section in the textbook, and I've broken it into 3 different sections. Yesterday we looked at the fundamental counting principle. Today we're going to formally learn about factorial notation and learn how factorial notation is connected to permutations. So we're going to be solving problems involving factorial, that should say notation. I don't know what it says on yours. It shouldn't be factorial notion. Does it say notion on yours? Or notation? It does say notion. Okay, thank you. And we're going to be solving problems using a formula for permutations involving NPR. That's how we say that notation, NPR. And we'll learn what that means in a little bit. So to begin with here, factorial notation, this is really review because we talked about this yesterday. If I said to you, you have 7 books and you have to stack them side by side on a bookshelf, or for that matter, stack them on top of each other in a stack, or put them in 7 different cabinets, it doesn't matter. The number of ways to do that using the fundamental counting principle would be the first place, whether it's the first cabinet or the bottom of the stack or the first place on the bookshelf, you have 7 choices, 7 books to choose from, and then 6, 5, 4, 3, 2, 1. And we abbreviate that using 7 factorial. This is a very important thing to know. The number of ways to arrange n items is n factorial, as long as there's no other conditions. So now this is something that many of you are going to look at, and you're going to say, well, why do we have to take something that I understand and turn it into algebra, which maybe is less meaningful to you? And the answer is because it's more useful. So when I say what is n factorial, whatever n is, you're going to take that number and multiply by 1 less than that number, and multiply by 1 less than that number, and continue to do that until you get down to 1. So if n is 12, you're going to multiply 12 by 12 minus 1, which is 11, by 12 minus 2, which is 10, etc. So this is a general way to, I guess, either write n factorial or expand it. N factorial is nice and compacted, but if I want to expand it and look at the factors of it, and that's why it's called a factorial, I have to write it this way. Calculate each of the following. So this is just on your calculator, we don't need to talk about how we're going to do this. You're going to go 5 factorial, you're going to go 10 factorial. 5 factorial is 120. Pardon me? Oh, you didn't get this handout. Okay. I'm sorry, Grant. My brain just skipped a beat. Is 5 factorial 120? Okay. Man, it's so embarrassing. I don't know what 10 factorial is. Again, we have that factorial function on your calculator. You go to the math menu. So you enter 10. You go math. You scroll over to the final column, which stands for probability, and you will locate that there. So it's 3,628,800. I think. I'll just double check that. Yep. So let's take a look at the next question. Why is 150 factorial over 148 factorial equal to that number? Well, first of all, try to calculate it on your calculator. You can't. 150 factorial is bigger than the largest number your calculator can use in its memory. I think your calculator can do 68 factorial. It might be able to do 69 factorial. I don't think it can do 70 though. I think 70 factorial breaks the bank. But you were expected. I mean, I could ask you on an exam, what is the value of 150 factorial over 148 factorial? And you should be able to figure it out. Let me give you a simpler example first. What if I gave you this? I said, everybody, I want you to think about this and figure out what 150 factorial divided by 149 factorial is. I want everybody to think about that. Think about what 150 factorial means. Think about what 149 factorial means. And see if you can tell me what 150 factorial over 149 factorial is equal to. Check. Does anybody know? Evan? It's equal to 150. Because, and this is not the example. Excellent. 150 factorial is 150 times 149 times 148 all the way down the line times 3 times 2 times 1. And we have over 149 factorial, but this is 149 factorial. So this 149 factorial, and I didn't bother, but I could have written on the bottom 149 times 148 times etc. down to 3, 2, and 1. Cancels with this, and you're left with 150. So if we do that, and listen very carefully to something I want to tell you here. What we want to do is start expanding the bigger factorial until we see the smaller factorial contained in it. Always. So 150 factorial is 150 times 149 times 148 times... And how many of you, I'm just curious, how many of you understand that I could have just done this at this point in time? Not all of you will understand that. So what I'm going to do is expand this out until I get 3 times 2 times 1. And I know we don't need to write the 1, but it's what we do. Okay? And then on the bottom, I have 148 factorial, but this is 148 factorial. So everything cancels except for the 150 times the 149, and unless I've made a serious error here, when you multiply 150 by 149, you're going to get 22,350. So maybe just double check that. Yes? Perfect. All right, so you knew this had to happen. This is a 30-level academic math course. It's algebraic in nature. We have to simplify n factorial over n minus 2 factorial. Of those 2 factorials, I want you to give some thought here. I'll give you about 10 seconds to think about this. I want you to give some thought as to which of those factorials is bigger than the other. Put your hand up and then down if you know. It's not a trick question, right? N is more than n minus 2, because when you take 2 away from n, you get a smaller number. So n must be a bigger factorial. So we are going to expand the larger factorial until we see the smaller factorial inside of it. N factorial means n times n minus 1 times n minus 2. How many of you see the smaller factorial already contained inside of it? Okay, it's the n minus 2 all the way down to the end. And if I wanted to, I could do this. There's nothing wrong with doing that. I prefer, though, to actually show ... times 3 times 2 times 1, and to say that this whole thing is n minus 2 factorial over the n minus 2 factorial you shouldn't have to, and I never will, take that n minus 2 factorial on the bottom and start writing n minus 2, n minus 1, or n minus 3, n minus 4, n minus 5. You shouldn't need to do that. Cancels. You're left with n times n minus 1, or maybe on a multiple choice exam, this is the answer. N squared minus n. Any questions with A? All right, B, n plus 3 factorial over n factorial. We need to expand the larger factorial until we see the smaller factorial embedded in it. This time the larger factorial is n plus 3 factorial. So what is n plus 3 factorial in expanded form? It's n plus 3 times n plus 2 times n plus 1. I keep reducing the factor by 1 regularly, every time. Times n, times, now we're subtracting 1 from n to get n minus 1, n minus 2, ... 3, 2, 1. And on the bottom we have n factorial. But n factorial is this series of factors, which will cancel with the n factorial in the denominator. Leaving me n plus 3, n plus 2, n plus 1. And I don't think we want to expand that. That's not the purpose in this course. Expanding that is a Math 9 or 10 idea. But you know, this could be a numerical response question where you're told that this is equal to n plus a, n plus b, n plus c, and asked to maybe write the 3 different values that a, b, and c could have, or maybe asked to write the sum of a plus b. Any questions with part B of this example? All right, n factorial over n minus 1. Now be careful here. That n and n minus 1 on the bottom are not factorials. They're just factors. So my whole strategy of expanding the bigger factorial until you see the smaller factorial kind of falls flat on its face, because there is no smaller factorial. But we can still expand the bigger factorial because we're curious about what's going to happen, or because what else are you going to do? Just stare at it? The only thing you can do is start to expand that n factorial, and you have n times n minus 1 times n minus 2 times etc. I'll go one more, all the way down to 3, 2, 1. And this is over n times n minus 1. So this time we're going to be canceling factors and not factorials. We can cancel the factor of n on the bottom with the factor of n on the top. Remember, you only ever cancel in an expression, a rational expression, factors on the top and the bottom. So they need to be in their own set of brackets being multiplied by everything. We can also cancel these. So what are we left with? N minus 2 times n minus 3 times n minus 4, etc., all the way down the line, which is n minus 2 factorial. Any questions with C? All right. So, permutations. I've already explained this to you yesterday before we even talked about Bobby Bear and the fundamental counting principle. But what a permutation is an arrangement of items. The word arrangement means order matters. Okay. If I'm going to arrange the flower pots on my deck in the spring, and I put, my azaleas in one location and my rose bush in another, that's a different arrangement than if I swap them, right? So order is important with a permutation. Whoops. As an example, how many different permutations of all of the letters of each word are there? So the only thing that's different with this question, everybody, is I'm using the word permutation. Yesterday, if I said, how many ways can you arrange all of the letters of the word Regina? You would have said 6 factorial, wouldn't you? I don't feel the need to write 6 blanks and go 6, and then there's 5 letters left, and then there's 4. We learn after a while that if you're arranging n items, the number of ways that it can be accomplished is 6 factorial. Ashmont has 7 letters, so the number of ways that I could arrange all of the letters of the word Ashmont would be 7 factorial. What those numbers are equal to is not important to our discussion. I think 6 factorial is 720, and 7 factorial is, I want to say 5040, but I didn't calculate that. That's just a number that popped out of my head. 5040? Okay. And I've already said this. I think I've said this at least once yesterday and now 3 or 4 times today. The number of permutations, well, I didn't say this yesterday because we didn't use the word permutations. But the number of permutations of n items taken all at once, that means all of the items have to be arranged, is n factorial. What about if we wanted, and this is at the top of the next page, what if we wanted to talk about the number of permutations from a pool of numbers, but we don't want to arrange all of them? And you could do this using the fundamental counting principle, and we will in a second. But in other words, what if I said we have 7 items, and we're going to only arrange them in groups of 4? And it's not a difficult problem. We could use the fundamental counting principle to do that, but we write it as 7p4. So what 7p4 means, and I'm going to rewrite this a little larger. What 7p4 means is this is the total in the pool of items, and this is how many are arranged. Now, I have heard many people pronounce this as 7pick4. Do not do that. Okay, we'll learn later the finer details of that, but pick seems to imply you're just grabbing them and not arranging them. And there's a word that's the same as pick, which is choose, and choose is the wrong word here. So what this is 7 arrange for, or 7 permute for. And it turns out it's equal to NPR, N permute R, N is the number of items in the pool, R is the number you are arranging at a time. It's equal to n factorial over n minus r factorial. That's what we will get. And this is on your formula sheet. And even though we can solve some problems without using it, we cannot solve all problems without using it. By the way, just a note, and you can try this on your calculator. Can you determine what 0 factorial is? It's 1, which doesn't make a lot of sense, does it? But it has to be 1 by definition, because if I said, what is NPN? Just think about this. I have n items and I'm going to arrange them all at once. You know what the answer is, right? It's n factorial. If I have 7 items and I'm arranging them all at once, it's 7 factorial. So we know that this has to give n factorial. When you apply this formula, you have on the top n factorial. On the bottom, you have n minus n factorial. N minus n is 0, so you get this. But if that's going to be equal to n factorial, 0 factorial by definition is 1. So I just want to get that out of the way. 0 factorial is defined. All right. Is this the next part of your lesson? I just want to make sure. Yeah. There is an example 3. Is it how many ways can we arrange 4 letters of the word Ashmont using the fundamental counting principle and then also using permutations? It's the same as this, but it says Ashmont. Okay, I'm getting conflicting messages here. I have a feeling I'm missing an example here. Oh, so it's how many ways can we arrange 4 letters out of the letters from the word Ashmont, but it doesn't say using the 2 methods. I'm going to do that using the 2 methods, however. So this is number 3. So we have the word Ashmont, and the answer is 7P4, right? There's 7 letters, and we're arranging them 4 at a time. So I could now take 7 factorial over 7 minus 4 factorial, which is 7 factorial over 3 factorial, which is, what did I say 7 factorial was? 5040? 5040. Over 3 factorial is 6, and you could certainly use your factorial button to calculate those. And my brain is not cooperating with me. Can you tell me what that works out to? 840? So the answer to this question is 840. Now, could we have just used our calculator in this way? And the answer is yes. 8. Go to your math menu and over to your probability menu, and hot dog, there's an NPR function. Now, I have a feeling in the TI-84, for most of you, what's going to pop up when you choose that, you'll have the 2 little boxes. Am I right? So I guess I will show that to you. I don't use this. I don't like the skin. I don't like the look of it. But when you go to your math menu here and to probability and choose NPR, maybe I'm wrong. How many of you, when you choose the NPR, you get 2 little boxes? How many of you don't on the TI-84? well, that's weird. Well, deal with it. Okay, if you don't have those boxes, you don't have those boxes. What I was going to say is when you do this on a TI-83, of course we wanted 7P4. It doesn't look right, correct? And some of you on the 84, it looks like that as well. You need to understand something though, that as soon as I put that NPR in between those two numbers, my calculator locks that as one piece. I don't need to put brackets around anything there. It knows that, for example, if I said times 8, it's not going to multiply 4 by 8 and then go 7P32. Anyway, we could do it this way. You get 840. You could use the Bobby Bear principle and say that we're arranging 4 items. There are 7 choices for the first, 6 for the second, 5 for the third, and 4 here. That gives you 840. And that goes a long way to explaining this formula. It's 7 factorial, which is 7 all the way down the line to 1, divided by this 3 factorial here. Kind of where the formula comes from. All right, I'm not going to use the fundamental counting principle anymore after this example. Example 4, license plates consist, I shouldn't have said that. We're still going to rely on the fundamental counting principle from time to time. In a particular country, license plates have 2 different letters followed by 4 different digits. What is the total number of plates using the fundamental counting principle? Well, I need 2 different letters, and I need 4 different digits. I don't think there are any restrictions, like we can use zeros, it doesn't say. Well, for the 2 different letters, it would be 26 times 25. Does that make sense? The first place on the license plate has any one of 26 letters, and then the second has any one of 25 because you can't repeat. And then this would be 10 times 9 times 8 times 7. And whatever that is the number. I don't want to be dismissive of the answer. Let's calculate it. And you should get this number, 3,276,000. Okay. How would we do it using the fundamental counting principle? Well, we are using permutations. The answer is we would do it a lot simpler. You need to pick 2 letters and arrange them. You need to arrange 2 letters out of 26. And you need to, out of 10 digits, arrange 4 of them. So if you run this through your calculator, 26p2 times 10p4, and we would never use the formula to calculate these. I mean, we would never write 26 factorial over 26 minus 2 factorial. This is where I really wish we had these factorials and NPR buttons right on the home view of our calculator. A lot quicker. Is this the final example? Okay, so I want to back up. Any questions about how we did number 4? Okay, solve this equation algebraically. Algebraically. This could be a written response. If it's not, I'll show you a very simple way to do it. NP4 happens to be equal to 28 multiplied by n minus 1 P2. Now I want you to look at your NPR formula. You can look on your formula sheet. You can look in your notes. NPR is equal to n factorial over n minus r factorial. This is the rule or the formula. The only problem is, and we've encountered this before, sometimes math problems don't match the formula perfectly. For example, everybody, if you take a look at the n in this formula, on the right-hand side of the equation, that n is actually n minus 1, isn't it? So I think it might be helpful for some of you to think of this formula this way. Think of it symbolically rather than letters, because if you start second guessing, because, well, I got an n here and there's an n minus 1 there, you might have a problem here. So we are going to apply this formula to the permutations in the question. For example, the left side of the equation is n factorial over n minus 4 factorial. This is equal to 28 multiplied by the second permutation will be n minus 1 factorial over n minus 1 minus 2 factorial, which I'm going to rewrite as n minus 3 factorial in the next step. So I have n factorial over n minus 4 factorial. This is equal to 28 multiplied by n minus 1 factorial over n minus 3 factorial. Now comes one of the most difficult things for me to try to explain. It's challenging for me. We have 4 different factorials there, right? We have an n factorial, we have an n minus 1 factorial, we have an n minus 3 factorial, we have an n minus 4 factorial. Think about this just for a minute. The biggest factorial is n factorial, which means each of the other factorials are inside of n factorial because they're all smaller. Right? So I could, and I don't want you to do this, I want you to just lay off on the writing for a second. I'm going to write in green what I could do and then erase it. I could expand the n factorial until I see the n minus 4. This is all the left side. Until I see the n minus 4 and say, well, this whole thing is n minus 4 factorial, and I can cancel them. I could do that. Does somebody want to explain why this is a bad move? And I don't know if any of you will see it right away, but this is going to cause a lot of heartache for me mathematically. Liam? I'm going to get a degree 4 polynomial equation. Now, can you solve a degree 4 polynomial? Yeah. We want to use synthetic division and the factor theorem and go poking around that way to solve it? No. So now listen to the part that is, it's not difficult for me to explain, it's difficult for people to understand. So I guess there's not really much of a difference. Does this make sense to you? Since we have 4 factorials, we will be able to put them in pairs and use each pair somehow to cancel 1 in each pair. But we want those pairs to be as close as possible to each other so that when we cancel things, we're left with fewer factors. Since these are 2 apart, if I expand the n minus 1 factorial to cancel the n minus 3, then I'm going to be left with 2 factors that contain n. I'm going to be left with quadratic. Okay? But I notice that these 2 factorials are off by 1. Wait for that to go away. Inside of the n factorial is an n minus 1 factorial, and everybody here should see by now that if we canceled n minus 1 factorial out of n factorial, you were left with n. You were left with only n. That's a heck of a lot better than being left with n times n minus 1 times n minus 2 times n minus 3. Similarly, if I look at these two factorials, they are 1 apart in terms of the argument of the factorial. The argument of one factorial is n minus 3. The argument of the other is n minus 4. So n minus 4 factorial is smaller than n minus 3 factorial, which means n minus 4 factorial is inside of n minus 3 factorial. And if we expand n minus 3 factorial and cancel the n minus 4 factorial, we'll just be left with the n minus 3 because they're off by 1. So I'm going to expand the larger of the blue, and this is where you can start writing. I don't know how far you want to go here, but this is n factorial. And I'm going to expand the larger of the two yellow factorials, which are 1 apart from each other in terms of the argument. I don't really have a lot of room here. I'll write really small. N minus 3 factorial is n minus 3 times n minus 2 times n minus 1, all the way down the line to 3, 2, 1. And then I have an n minus 4 factorial here. I have a feeling that some of you were maybe a little confused by the fact that I have these pairs. I have a blue pair where one is on one side and one is on the other, and I'm saying I'm going to cancel. Well, I can divide both sides of this equation by n minus 1 factorial to cancel those. They don't have to be on top of each other. They can be both on the top on opposite sides of the equation. Similarly, I have an n minus 4 factorial in the denominator here. If I multiply the left side of this equation by n minus 4 factorial, and I multiply the right side of the equation by n minus 4 factorial, whoops, I expanded the wrong one, didn't I? No, I didn't expand the wrong one, but I made a horrible error here in expanding n minus 3 factorial. I'll give everybody a second to look at it and see what it is. Jason, can you tell me what I did wrong here? Do you know? This is getting larger, right? And it should be getting smaller. So I should have written n minus 3 and then n minus 4, n minus 5, etc. down the line to the end, 3 times 2 times 1. How many of you caught that as I was writing it? Okay, that's good. Sorry about that. So the n minus 4 factorial, I can multiply the left side of the equation by n minus 4 factorial to cancel that denominator. And when I multiply the right side of the equation by n minus 4 factorial, the n minus 4 factorial in the bottom cancels, leaving just n minus 3. Let me rewrite this so that we can see it in a clearer light. All we're left with on the left is n, and on the right we're left with 28 over n minus 3, which is a fairly basic equation to solve. Multiply both sides of the equation by n minus 3 and get n times n minus 3 equals 28. Recognize this is going to be quadratic because n times n is n squared, so expand it out. You could do a lot of steps at once here. Since it is quadratic, I should zero the equation. And factor. Any of these problems where you have a factorial involved or you have permutations involved, where n is something you're trying to find, if it devolves into a quadratic, it has to be factorable because n has to be 0, 1, 2, 3, 4, etc. And there's a bigger restriction that we'll look at in a second. So what are two numbers that multiply to give negative 28 and add to give negative 3? Unless I'm mistaken, they're negative 7 and 4, which means the mathematical solution to this equation is n equals 7 and n equals negative 4. But we don't normally call them extraneous roots. One of these answers is impossible. I guess you could call it extraneous. Which one is not possible? Zebi, do you know? The negative 4. And the reason is, as soon as you start to put negative up here, and you ascribe a meaning to, say, np4, and you have negative 4p4, you're saying I have negative 4 items, and I'm going to arrange them 4 at a time. I don't even know what that means. By the way, so the answer is 7. Are we good with that? By the way, in terms of factorials and probability theory, which is what we're dealing with, n's can be 0, 1, 2, 3, etc. But I'm only bringing this up because some people are curious about factorials and they start poking around on their calculator. If you try to take, say, 1.2 factorial, you get an error. But if you try to take 0.5 factorial, you don't get an error. So there's something mathematically more sinister about factorials, more involved about factorials that you would learn about in a math degree in university. Okay, it's more involved than just multiplying numbers together. Now, what if that were a multiple choice question? Or let's say a numerical response question, because multiple choice, you could just test them all, right? Well, you could do this. You could put in for y1, x p4. For y2, you could put 28 multiplied by, we do need the n minus 1 or x minus 1 in brackets to say that that's the total number of items that we are choosing to arrange from. 2, graphically it won't work. You won't see graphs because these expressions only exist in certain points. It's not going to connect them. But I can go to my table setup, start at 0 and go up by 1 in automatic mode, double check because I didn't do this to make sure I've entered it correctly, and I think I have. Go to your table, and we want these two columns to be equal. You notice they're equal here and here, but n cannot be 3 in high school. Why can n not be 3? Because then this would be 3p4, and I'm asking you to arrange 4 items out of a group of 3. I guess it could be 3. How many ways can you arrange 3 items out of a group of 4? Or 4 items out of a group of 3, rather. You can't do it, so the answer is 0. But if we continue in our table, you will see that at 7, they are both equal to each other. Nice, clean method of determining the value of the variable that makes it work. But you can't graph them and find a point of intersection. Any questions with that last example? Sorry for my befuddlement there in expanding the n minus 3 factorial. Again, the numbers should always be getting smaller. Okay. And again, you're always expanding the bigger of the factorials to cancel the smaller of the factorials somewhere else. So some problems that you can practice are on page 10 of your unit handout. You got about 20 minutes or so here roughly.